going to work out an example using conservation of angular momentum. I have a merry-go-round with a known mass and a radius, so we can calculate its rotational inertia, and it's initially going at a half of a revolution per second. At some point, while it's going with that angular momentum, a person steps onto the outer edge, and we want to find how fast the merry-go-round and the person together are spinning then. This is actually similar to a perfectly inelastic collision, because after the person steps onto the merry-go-round, they're going to move together, so they have the same angular speed after the person steps on. And we'll see that our intuition from perfectly inelastic collisions and linear momentum holds up for the case of angular momentum as well. So in the initial state, I'm going to have the person is at rest and all the angular momentum is in the merry-go-round. So we'll need the rotational inertia of the merry-go-round and the initial angular speed. We want to convert that from being in a revolution per second into radians per second, because we're going to want to use omega to do other calculations. And those are only going to be possible if we're measuring angles in radians. So the merry-go-round's rotational inertia is a solid disk. So I have a prefactor of a half, mass of the merry-go-round, and radius of the merry-go-round squared. So it's going to be a half 200 kilograms. And its radius was 2 meters. So that's going to give me the rotational inertia of 400 kilogram meters squared. And the initial angular speed omega I, 0.5 revolutions per second. It's a pretty good clip. And we know that 2 pi radians is equal to 1 revolution. So that's going to be conveniently pi radians per second. So our initial angular momentum that's going to be conserved is 400 kilogram meters squared times pi radians per second. Going to be 1260 kilogram meters squared per second. And we don't have a derived unit at MKS for angular momentum, but it's going to have units of kilogram meters squared per second, and I dropped the radians because it's dimensionless, and I can. So then a person with mass 50 kilograms, so a little person, steps on the outer edge. How fast does our merry-go-round spin now? So if we take our system to be the person plus the merry-go-round, the force of friction and the normal force that each are exerting on the other, the person and the merry-go-round, are internal to the system. So they're not able to change the angular momentum of the system. isolated, so I can say initial angular momentum is equal to the final angular momentum, ignoring torques caused by air resistance or any torque caused by friction in the spindle on the merry-go-round. So what does that tell us? Looking at the final angular momentum, we're going to have the rotational inertia of the merry-go-round, which hasn't changed, but now the person is rotating along with the merry-go-round, so they'll have a contribution to the rotational inertia, and it has some unknown final angular speed. Can write out what that is. The merry-go-round hasn't changed, so that's still 400 kilogram meters squared. For the person, their mass at 50 kilograms and they're at the outer edge, so they're going to make a contribution of mr squared. So it's going to be 50 kilograms times 2 meters quantity squared times omega final. And that's going to be 600 kilogram meters squared times omega final. So conservation of angular momentum and solving for omega final. Omega final is going to be the initial angular momentum divided by the rotational inertia of the merry-go-round plus the person, which we just found is 600 kilogram meters squared. I'm going to have 1260 kilogram meters squared per second over 600 kilogram meters squared. So that's going to give us 2.1, and then everything cancels out except for the 1 over second, so I'm going to pop a radian in. So it's slowed from pi radians per second to 2.1 radians per second. If we wanted to convert that over, we'd find that that's a third of a revolution per second. All right, now I want to look at the inelastic collision part of this. I'm going to look at the change in kinetic energy for the merry-go-round and the change in kinetic energy for the person. If it were an elastic collision, then kinetic energy would be preserved. I'm going to see what happens in this case. So for the merry-go-round, change in kinetic energy of rotation is going to be the final kinetic energy of rotation minus the initial. So that's going to equal a half. It's the same rotational inertia for the merry-go-round. Omega final squared minus omega initial squared. If we put in our values, a half at 400 kilogram meters squared. And this is why it's going to have to be in radians, because I can't get an energy in joules unless omega is in radians. So the merry-go-round lost, let me work that out, 1090 joules. Now what happened for the person? If kinetic energy was preserved, then that person would have gained 1090 joules, right? So let's look at what actually happened. So a half rotational inertia of the person, omega final squared, minus a half rotational inertia of the person, omega initial squared. And they weren't moving to begin with, so I can drop that term. So it's going to just be their final kinetic energy of rotation. We have the values for that. It's a half, 200 kilogram meters squared, and they're moving along with the merry-go-round. So 2.1 radian per second quantity squared. They gained 440 joules of kinetic energy. But this is not a problem. All this is saying is that the person did more work to slow down the merry-go-round than the merry-go-round did in speeding up the person. And since there's no reason for the displacement of the merry-go-round to equal the displacement of the person as they're in the process of stepping on the merry-go-round, that's perfectly fine. That is just what it works out to be.